Hello, please try again.
Hello? It's okay.
Okay, hello everyone. Let's start the afternoon session. The first speaker is D'Andrea, and will talk to us about dark matter direct search with the Xenon experiment. Okay.
Okay. Thanks all. Thanks to the organizer for this conference and give me the opportunity to present the talk here. I'm Valerio D'Andrea. I'm coming from the University of L'Aquila and the Laboratori Nazionali del Gran Sasso in Italy. I'm giving an update on the status of the Xenon experiment. So here a picture of our collaboration in one of the last meeting that we have. One of the main goal of our collaboration is to search for dark matter using a liquid xenon detector. So this is our collaboration. We have 28 institutes from all the world with more than 170 scientists. As I said, the location of our experiment is the laboratory of the Gran Sasso, the underground laboratory of the Gran Sasso. You can see here a map of the laboratory and also the position of our experiment. And here you can see a picture of how our experiment looks like. Here in the center you can see the big water tank that we have. This is an area of something like 10 meters, and then here in the right you can see the 3-floor building that we have close to our experiment, where we have all the system and electronics that we need. So Xenon is using a particular kind of detector that is a TPC, a time projection chamber, that is a TPC with a dual phase xenon. You can see here a sketch of our detector. The main part of the detector of the TPC is liquid xenon. And then we have also a layer with gas xenon that is the layer on top of the TPC. When a particle is entering this volume, is releasing energy and is producing a first scintillation light signal that is the signal we call S1. That is also signed here in the liquid xenon. And then what is happening in that the electrons are drifted on top of our TPC and are reaching the gas phase when we have a second signal, a second scintillation signal, that is what we call S2. In this TPC we have electric fields. In particular, we have 2 electric fields that are provided by the installation of 3 electrodes in particular. Using S1 and S2, we can reconstruct the energy of the events that is originating the energy release. And an important point is that we can use the ratio between the 2 signals to distinguish between background and signal events. During the year, we had an evolution of this kind of detector. We started from a very little detector with a very little dimension of something like 20 centimeters with the so-called experiment called Xenon 10. Then we had Xenon 100, and then the most recent Xenon 1 ton that is finished something like 3 years ago, and now the present experiment that is called Xenon N-ton. During these 4 steps, we had an increasing of the dimension of our detector and, of course, of the active mass of the liquid xenon that now is something like 6 tons. And, of course, we increased our sensitivity in the search of the dark matter. Here in this talk, I'm saying something more about the results obtained with Xenon 1 ton and the state of art of Xenon N-ton. For the future, there is a program to build an even bigger detector that is the new collaboration is called Darwin. And the program is to build a huge TPC with something like 40 tons of liquid xenon. So now I say something about the experiment Xenon 1 ton. Xenon 1 ton build a cylindrical TPC with dimension both diameter and depth of 1 meter. Here you can see a picture of the TPC, and you can see the picture of the 2 PMT arrays that are mounted on the bottom and the top of the TPC. The active mass was 2 tons of liquid xenon, as I said, with a drift field of something like 100 volts per centimeter. In total, we had 248 PMTs. Using the position of the PMTs, we can perform an XY reconstruction. We had excellent performance with this kind of detector, and we obtained a resolution of 1.6% at 2.5 MeV and 6% at 4 kV of energy. The TPC is installed in a water tank where we have a Cherenkov muon veto, and for the experiment we designed and installed a novel system for the xenon cryogenics, for the xenon storage, and for in particular, that is most important, for the purification of the liquid xenon. The idea was to build all these infrastructure that then can support also the next stage, that is the experiment that currently is running, that is Xenon N-ton. So using the Xenon 1 ton data, we had a lot of scientific results that I'm listing here. I'm not, of course, entering in the details of all these results. I'm just giving you an idea of the results that we obtained. This is the main results in the search of dark matter. And then one of the last paper that we published that is about this excess that we observed in the electronic recoil spectrum. So these are the results regarding the dark matter search, in particular in the WIMP nucleon spin-independent elastic scattering, where we had something like 280 days of data with a fiducial mass of 1.3 tons, that is corresponding to an exposure of something like 1 tons per year. We had an ultra-low background due to electronic recoil, and we observed no excess over the background. With this data, we were able to set a new limit in the WIMP nucleon cross section that was something like 7 times more sensitive than previous experiment. The minimum of this limit was at 30 GeV. That is the most stringent upper limit. At 30 GeV, we have a value of 4.1 times 10 to minus 47 centimeters square. Another important results that, as I said, is one of the last publication of Xenon, is the observation of an excess that is corresponding to 3.3 sigma fluctuation. This excess is observed in the electronic recoil spectrum, as you can see from this plot here, where I'm reporting the energy region between 0 and 30 kV. Several hypotheses were made to explain this excess. One of the first one that was excluded is that this could be caused by a leakage due to argon-37, but a lot of other hypotheses that I'm listing here. Of course, I'm not a theorist, so I don't know much more about all these hypotheses, but this excess can be explained using solar axion, an anomaly in the neutrino magnetic moment, and also can be explained with models including bosonic dark matter, like axion light particle or dark photon. Also, this kind of excess can be explained by the presence of the tritium, in particular by the beta decay, and in particular with a concentration of 6.2 times 10 to minus 25 mole per moles of xenon. This hypothesis, with the data that we had in Xenon 1 ton, cannot be confirmed or excluded, but including this concentration of tritium, we have that the hypothesis of solar action and the neutrino magnetic moment are decreasing in significance. So up to now, the mystery is unsolved, and what we are doing, we are expecting the new data from the new experiment that is Xenon and Photon. So now I will tell you something more about this new experiment that basically is an upgrade of Xenon 1 ton with a larger TPC, with something like 6 tons of liquid xenon and something like 500 PMTs. Here you can see a picture of this big TPC and of one of the 2 PMT arrays. And this is a beautiful picture of one of the electrodes that are providing the electrical field that we have inside our TPC. An important upgrade of Xenon and Photon is the introduction of an active neutron veto in the external part of the TPC, as you can see here from this sketch. In the neutron veto, we have gadolinium doped water read by PMTs in the surface of this volume. The main goals of the Xenon 1 ton is also regarding the reduction of the background, in particular with the goal in the purification of the liquid xenon and regarding the reduction of the background coming from the radon 222. So the Xenon and Photon experiment was successfully commissioned at the Gran Sasso. Last year we had the installation of the TPC, the installation of the new neutron veto. We can see the neutron veto here in this picture here. And we also tested all the subsystem between the end of last year and the start of this year. We also acquired some commissioning TPC data in the first months of the current year. The current situation is that now we are taking the first science run data, and the initial performance are quite good regarding the light collection. That is better than what we had in Xenon 1 ton. An improvement also in the energy resolution with a value of 7.6 at 41.5 keV. That this is measured using a calibration source of Krypton 83, and we have excellent performance also for the PMTs. Also, that this is one of the most important results of the first months of data taking is regarding the background, the purity that we have in our experiment. We have an ultra low radon emanation, and we are measuring an activity of radon that is something that is less than 2 microbecquerel per kilogram. And we hope that this factor can be reduced by a factor of at least 2. Here I'm reporting a preliminary background that we have in the first science run that is now ongoing in these months. We can see from this background the principal gamma line that we have in our spectrum. The spectrum is going from 0 to 3 MeV, and we can see the two. We use a blind analysis for both the dark matter that is searched in this low energy region here, and also we are searching for the neutrinoless double beta decay in this region here. The neutrinoless double beta decay can be from the isotope of xenon 136. So in the first part, in particular in the first part of our analysis, we want to address the low energy electron recoil excess problem. So what is the expected sensitivity of Xenon 1 ton? What we want to do, we want to improve of at least of an order of magnitude the limit on the WIMP nucleon. This is the spin-independent WIMP nucleon cross-section. We want to put a limit that is 1 order of magnitude below the limit of Xenon 1 ton, as you can see from this plot here. and in particular, the minimum of this limit at 50 GeV of WIMP mass with a value of 1.4 times 10 to 48 centimeters square. As I said, we want to perform a detailed investigation on the excess that we observed in Xenon 1 ton, and the study that we performed are suggesting that after a few months of data taking, we can differentiate the hypothesis of the solar action from the tritium background hypothesis with an high significance level. Okay, and the conclusion of my talk, as I said, Xenon is using a time projector chamber with a dual phase that is based on a dual phase Xenon, and this is the leading technology up to now in the field of the direct dark matter search. The last results that we published are using the Xenon 1 ton experiment with 2 tons of liquid xenon as active mass. This experiment made a lot of improvements in the years, both regarding the results of in the dark matter field and both also concerning the technological improvements regarding low background experiment. The current phase that we are running is called Xenon N-ton, that is even a more powerful tool to say something more about the dark matter. And in particular, Xenon N-ton will be able to answer the low electron recoil excess problem. As I said, Xenon N-ton now is with the data taking ongoing, so we will have soon new data and new paper to say something more on dark matter. So thanks for the attention.
There are questions already. Please go on.
Yeah, hello. It works. Good. Thanks for the talk. Can you go to the slide before? Okay. So what is the timeline? Maybe we set it for the Xenon and NT. If I look at the left plot, I mean, when would I expect to be there?
Yeah, Xenon N-ton wants to reach this. Yeah, I missed the wants to reach these 20 tons of per year of exposure, and we have an active mass of 6 tons. So this means 5 years of data taking.
Okay. And the second question, I mean, you have some uncertainty bands here. Yeah. So what is the source?
Yeah, the source is the background level that we can reach. So I said a lot of time during my talk, the background level and the purity of the liquid xenon is one of the main point of this kind of experiment. So the uncertainty is related to the background. We can reach a higher limit if we have a low background. So this is the goal of.
Okay, I mean, just a comment. I'm asking this because all these dark matter results, I'm not only presented by you, by everyone, are usually presented having a specific cosmological model in the back of the head. And what would also be interesting, I tell it to you, I tell it basically in all talks I see like this, would be to see how this is varying if something changes not on the experimental level, but let's say in the theory prediction, or if some other astrophysical procedures would be assumed. I mean, some of these things you can do by varying parameters within theoretical tools, I know, but it would be nice to have as an add-on some uncertainties, because these can in principle be quite large and for sure exceed this, and somehow it goes into the result, I mean, not into the experimental output, but into this experimental presentation.
Yeah, you mean the situation is not so fixed, like you say in the theory.
Yeah, exactly. So this, I think, would be quite helpful, because these constraints are very strong for very many years, so they are sometimes the most constraining thing. This would be nice. Okay, thanks.
Okay, thanks.
Okay, is there any other question in the room? Okay. Online, please. Yair.
Okay, thank you. One question. Thank you very much for your talk. So, could you compare the sensitivity of xenon and tone with the LZ? Just kind of projection.
Please, can you repeat a little bit louder with your microphone closer to your mouth?
Okay. Look, can you compare the sensitivity of n-tone projected, xenon n-tone with the LZ calibration? Well, kind of, are they similar?
I think the results of Xenon 1 tone, I don't remember if I put, yeah, you can see here the last result from LAX, and the results published by Xenon 1 tone is lower than what LAX obtained.
No, I'm talking about the LZ.
Sorry, I think that you're saying about the Xenon n-tone sensitivity. Yeah, I don't remember, but I think also in this case the sensitivity of LAX is a little bit higher than Xenon n-tone.
I see. Okay. Yeah. Any new? The question is, if you observe any confirmation with your n-tone detector, the confirmation of this anomaly, which we observe.
We are in data taking since something like 2 months, so we don't have fresh data with the new analysis up to now. But I think we will have soon. I don't know. I think at the start of the new years, and one of the main goal of the first analysis will be address this excess. So this is the main goal of the analyst of Xenon.
Okay.
So let's say the start of the new year, we will publish a new paper probably.
Thank you.
I don't see any more questions, so let us thank the speaker again. The second talk. The presenter is Piazza Federica, and she will talk to us about the search for dark matter in association with energetic photon in PP collisions at square S equals 13 TeV with the Atlas detector.
Good enough? Yes? Okay. Okay, for this. Okay. Okay. Yes, sorry for the long title. Hello, I am Federica Piazza. I am a PhD student at Università degli Studi di Milano, and I am working in the Atlas experiment. I will describe today a search for dark matter in, as you already said, in a final state with the energetic photon and missing process momentum with the Atlas experiment. Okay, so we all know that about 27% of the universe is composed by dark matter, but despite the several evidences of its existence, non-gravitational interaction between dark matter and ordinary matter has never been confirmed so far, and so its properties are still largely unknown, and there are several possible candidates in a wide range of masses, and so it's important to to keep on with the complementarity of approaches to dark matter detection. And in this context also, one of the possible strategies is production at collider, so production of dark matter particles from standard model particles collisions. And the main assumptions for production at collider, of course, is that dark matter particles do interact with the standard model particles through non-gravitational interaction. And this is the only way, of course, they can be produced at collider. And in this case, they can, of course, also be produced in the proton-proton collisions at LHC. The other assumption is that dark matter particles are stable and weakly interacting, and so they will not interact in the Atlas detector, for example, and they will not decay inside the detector. So they can't be directly observed, but if they are produced in association with a visible standard model particles, they can be observed in form of missing transverse momentum, because we will have a visible transverse momentum which is not balanced in the opposite direction, and so this unbalanced, which is the missing transverse momentum, is the main signature of dark matter in the Atlas detector. And of course, there are also standard model processes where we can have high ATMs, for example, if we have neutrinos. So what we look for is an excess of event with high ATMs with respect to background expectations. So this analysis uses the full run-2 dataset, so data collected between 2015 and 2018 for a total integrated luminosity of about 114 inverse femtobarn. And this is an extension of a previous analysis published with the lower statistics at 36 inverse femtobarn. The main interpretation we provide is in terms of WIMP production in a simplified dark matter models, where the dark matter particles are Dirac particles produced in this S-channel process with the vector or axial vector mediator. And the three parameters of the theory are the mass of the mediator and the dark matter, and the couplings of the mediator to the standard model and to dark matter. While the mediator width is fixed to the minimal value, assuming that the mediator can decay only into dark matter particles or quarks in this case. We also consider for the first time an interpretation in terms of axion-like particle production. In this case, we consider an effective field theory. And the axion-like particles is an additional singlet scalar, and the three parameters in this case are the CW, which is a parameter related to the coupling of axion to the W boson of the SU2 gauge, and the scale of the theory. And for this analysis, we consider the couplings of the axion-like particle to photons as negligible given the existing constraint. And this allows us to get fixed value of the coupling to B boson given for a given value of the coupling to the W boson. The signal region is defined requiring a high energy photon, at most one jet and no leptons. And the photon and the jet, if present, have to be well separated from missing transverse momentum. And we define 7 signal regions in bins of ATMs, 4 inclusive one and 3 exclusive ones. And these have been optimized with respect to the past analysis where we had only 5 bins. And also we increased the lowest threshold of ATMs from 150 GeV to 200 GeV to suppress the background from fake ATMs, which is events with ATMs coming from mismeasurement, in particular of jet and photons, rather than undetected particles. And important to suppress this background is also this Carton ATM significance, which is a variable which has a high discrimination power between real ATMs and fake ATMs. And also this, here we, with respect to the past, we are considering a more refined definitions which takes into account the resolution of each object entering the ATMs calculation, and these cut also have been re-optimized. And finally, we also included an explicit tau veto to further suppress this background with the W or Z decaying to tau. So in the end, in the signal region, this is the background composition. The dominant background is the irreducible background is Z decaying to neutrinos. Then we have the W and Z decaying to leptons if the leptons are not detected. This gamma jet is the fake ATMs background I was mentioning before, and then we have electron and jet misidentified as photon, which we call fake photon. For all the background with the real photon, we use Monte Carlo simulation and control regions that I will describe later. For the fake photon, we use data-driven estimates, because this misidentification between electron or jets and photon is not particularly well modeled in Monte Carlo simulations. So for the electron faking photon, we derive this electron to photon fake rate as a function of heat and PT from data, and in particular from a sample of the Z decaying 2 electrons. So we count the number of events with the electron-photon pair, where the photon is actually an electron, and with the electron-electron pair. And we obtain this number through our signal past background fit on the mass spectrum of the Z. So invariant mass of the electron-electron pair or electron-gamma pair. And then we use this scale factor to rescale the yields in probe electron control regions, which we define from the control region and signal region of the analysis by replacing the photon with an electron. For the faking photon, we use this two-dimensional sideway method based on 2 ideally uncorrelated variables, defining 4 regions, 1 signal region enhanced with the true photon, and 3 control region enhanced with the jet faking photon. And the 2 variables are the isolation of the photon, which gives an estimate of the how clean is the environment around the photon, and the identification. So tight are good quality photon or better quality photon, while not tight are loser quality photon. And the number of jet faking photon can be obtained this way, where NA sig is the number of events with true photons in the region A. And in this equation here, the R and the C are coefficients obtained from Monte Carlo sample, WZ plus gamma for the C and WZ plus jet for the R. And the C takes into account the possible leakage of true photon in the control regions, while the R takes into account the possible correlation between isolated and tight regions. For the other background, as I mentioned before, we use a Monte Carlo simulation and normalize the prediction to data through a simultaneous likelihood fit in the control region. So each control region is defined such to be enhanced with a particular background. So we have this low mass control region for gamma jets, 1 muon control region and 2 muon O2 electron control region, respectively for a W or a Z gamma, where we require exactly 1 muon or 2 muon O2 electron. And we also define the ATMIS to considering the electrons as invisible particles in order to reproduce the signal region kinematics. And once we extract the normalization factor from the fit, we can extrapolate them to the signal region with this formula. And systematic uncertainties are included as nuisance parameters with a Gaussian constraint, and they are treated as correlated among all the control region, with the exception of the uncertainties from fake photon estimates, data-driven estimates. No, sorry. So coming to the results, in this table, the uncertainties are summarized in different bins. In the first row, the statistical and systematic uncertainties. In the second row, only the statistical uncertainty. And you can see that the statistical uncertainty is dominant with respect to the systematic ones. And this is because systematic uncertainties are partially cancelled out thanks to the simultaneous likelihood fit method. And in the end, the dominant systematic uncertainties are the ones from the data-driven estimates and the one from JET's calibration and resolution. In this plot here, you can see the distribution of ATMIS after the fit. So different colors have different background. Then we have this dashed line for some example of signals and data. And from the ratio plot, you can see that there is no excess with respect to standard model expectation. The bottom plots are a summary of the results in all the control region also of our fit. And we perform a single beam fit, which is done simultaneously on control regions, but separately in each bin of ATMIS. So here we have the signal region and control region for the first inclusive ATMIS bin, for the second one, third one, and fourth one. For the simplified shape fit, the fit is done simultaneously on all the control regions in all the ATMIS bins. And so here we have the photon jet control region, the 4 bin, these are the exclusive bins of 1 muon, 2 muon, 2 electron, and signal region. So this part of the plot is basically the same as this plot. And in the bottom panel, you can see the significance in each bin. So since we observe no excess, we can set the exclusion limits. And for the simplified dark matter model of wind production, they are shown in the mass of the mediator, mass of dark matter plan. And we consider axial vector mediator and vector mediator. And we also consider different couplings to of the mediator to the dark matter and quarks and leptons. So here we have no coupling to leptons. Here we have some small coupling also to leptons. And the excluded area is the one below the curve, and the yellow band takes into account both the statistical and systematic uncertainty. We can also translate these results in the mass of dark matter cross-section of the dark matter nucleon scattering in order to compare with direct detection experiment. And in particular, we can compare the axial vector mediator case with the spin-dependent direct detection experiment and the vector mediator with spin-independent ones. And you can see that our limits are more sensitive than a direct detection experiment for the axial vector mediator case. And they're not so much competitive for the vector mediator case, but still we can exclude this region here for very low masses. For completeness, this is a comparison also with all a set of other analyses done in Atlas for these S-channel simplified dark matter models. So these here are the so-called mono-X analysis, and the pink one is the monophoton analysis I'm talking about. And then we have all these results which come from the lepton and dijet searches, which are basically searches for the mediator, and in particular for the decay of the mediator into 2 leptons or 2 jets. And so these to show that it's a common effort in all the collaboration, and the single analysis maybe doesn't tell much, but all the analysis together can give a better understanding. The other exclusion limit I mentioned in the first slide is this limit on axion-like particle. Here we have the scale of the theory. Here we have the coupling to the W boson, and the excluded area is the one above this line. So basically, we can exclude the values of the ratio above 1.2 times 10 to the minus 4 inverse GeV. Finally, we provide exclusion limits, also model independent. This is useful to reinterpret the analysis in terms of models that we are not directly covering in our analysis. And in particular, here you can see for the different means the limit on the visible cross-section of physics beyond the standard model. Here the acceptance, the A is the fiducial acceptance. So basically not taking into account the detector effects, and the epsilon is the detector reconstruction efficiency. So we can go from the visible cross-section to limit on the fiducial cross-section just by dividing for this value reported here. So to conclude, this analysis has been performed on the full run 2 dataset. So there is an increase in statistics with respect to the previous results, and also some improvement in the selection, and for example, in the definition of the atomic significance. No excess have been observed with respect to the standard model expectations. So we set limits on these simplified dark matter models. Basically, dark matter masses up to 400 or almost 600 GeV are excluded for axial vector or vector mediator, with masses among 1.5 TeV to basically 1.5 TeV, and this is pretty much dependent on also on the coupling constant we choose. We have these limits on the axion-like particle production, which we are providing for the first time in this kind of Atlas analysis, and we can exclude the cross-section of physics beyond standard model between 0.5 and 2.5 inverse femtomal, depending on the ATMIS bin we are considering. Thank you.
Thank you very much. Do we have any questions? Yes. Gregory. Thank you very much.
Thank you. Maybe you have said, but I missed it. Those exclusion limits for the dark matter and mediator depend on the couplings.
Yes.
Can you just recall what are the couplings that you assume?
Yes.
Mediator to the standard model particles.
Yes. Okay. So actually, there are some recommendations to decide what couplings to consider. So there was a forum joining theorists and experimentalists and phenomenologists and experimentalists from Atlas and CMS, which discussed about this model and provided these recommendations, basically.
Thank you.
Let us go to the next one. Next question.
Thanks for the talk. Just maybe it's here in this plot, but I cannot see it. Do you compare with the, let's say, reasonable? Can you hear me? Okay, now yes. So maybe it's already in this plot, and I just don't see it. Do you compare with the relic density from the?
Yes, it's in the plot, but it's not particularly visible.
So those are the lines of the
Yes.
of the relic density. So you also
Yes.
give constraint on the dark matter mass directly, right?
Yes, I mean, sorry?
In terms of the mediator mass and the splitting with the dark matter.
Yes. So, okay, we can say that, first of all, this, for example, here we have this curve for the relic density. That means that below this curve, we will have a dark matter overabundance. So it's it means that this model would not be consistent with the relic density, assuming a freeze-out production mechanism. So this is the idea. But since these results are depending on the couplings and so on, the fact that this area is excluded by relic density is not does not mean that this model is excluded a priori.
Yeah, okay. So
Changing the coupling, maybe the situations would change.
thanks, Ceci.
Okay. Question from the room, please.
For instance, on this plot, the lower end of the mass is at 0. So is it really 0, or what
Yeah.
is the lower end?
Okay, we checked that basically we simulated signals down to mass of the dark matter of about 10 GeV, and then we, with the full simulation, okay, then we checked that for lower masses, going down to I think 10 MeV, something like that, the situations didn't change, so the results didn't change. I don't exactly remember down let's see. Yes, I think it was 10 MeV.
Mm-hmm.
Okay, and we saw that the results didn't change basically in that range. So we can assume that we can extrapolate also a bit lower.
Mm-hmm. Thank you.
Okay, I see we have one question from a remote question. Please go ahead.
Yes, thank you. Thanks so much. That was a very, very interesting talk. One thing that you may have mentioned, but I missed, was that you presented your plot for a lot of different kinds of mediators, but none of them were cases.
I can't hear you very well.
Sorry.
Hello, we can't hear you. Please,
Oh.
can you try?
Can you hear me better now? Can you hear me?
It's better now. We'll see.
It's better. Okay, fantastic. Yeah. I just wanted to ask about the scalar mediator case, because in kind of inert cascade case, you could also have exactly the same signal mediated with a scalar. Do you have any exclusion plots for scalar mediators?
No, we don't have. And I think in the monophoton final state, I mean, this final state would not be particularly sensitive to the scalar mediator cases. Yes, model with scalar mediator. Because if I remember correctly, the assumption is that there will be a coupling, kind of Yukawa coupling between a scalar mediator and the dark matter quarks, and so this would lead to kind of suppression of the cross section, and one of the dominant processes would be at one loop. I'm not completely sure about this, but I remember something.
Yeah, it definitely would be a loop process. Yeah. Great. Thank you.
Thank you.
Okay, thank you. Let us thank the speaker again. And let's go to the next talk. It's by Yundini, University of Basel, and freezing produced dark matter at high temperatures. Please.
When this I just go this one. Ah, okay, thanks. Okay, great. First of all, I would like to thank the organizer for the opportunity to join the conference and be here in person. It's 2 years that I do not deliver a talk in person, so I'm really happy to do that. And so in this talk, I will report briefly on a paper in collaboration with Jacopo Ghieri. And we basically reviewed just a bit, and for some particular models, the effect of the high temperature regime for freezing, which is usually kind of overlooked on good reason and good argument, that I'm going to show in the following. So you know that as soon as you insist on the dark matter being a particle, you have many and several candidates from beyond the standard model physics. However, as soon as you pick your favorite and you have your Lagrangian in terms of masses and couplings of the dark matter within itself and with the standard model, you have to comply with the relic abundance, which is a quite accurate prediction. And so you have to pick according to your model construction and production mechanism that link your Lagrangian with this observable. And usually this production mechanism happens in the healthy universe. We heard of it in many talks already, freeze out or gravitational production for dark matter and freezing, and I will insist in this talk on the freezing mechanism. In this case, dark matter never reaches thermal equilibrium. The couplings are so small with the other degrees of freedom in the plasma. And if you start and you assume a vanishing initial abundance, the plots that you usually see is that where the dark matter y-chi in terms of the yield is 0, and it grows up along the thermal history of the universe. With a very simple model like dark matter being this Dirac fermion here coupled to a scalar, basically the dark matter is produced by a parenting particle here, the scalar, which is assumed to be equilibrated, and then along its decay is indeed produced until the freeze out. The freezing of this part here. And if you just change the scale of the plot, you may appreciate now why this is usually called infrared freezing with renormalizable interaction like this here, because basically the dark matter, the relation, the yield here, just starts to be increasing where the temperature is of the order of the in vacuum masses of the particle involved in the processes, either the dark matter or the parenting particle, for example, here the scalar. So you see that this big rise happen here, and nothing interesting happens at high temperature. This has to deal with the ticking clock in the universe, which is the Hubble rate. So you have to wait long enough for this process to be actually effective, and then freezes in and stay constant because the equilibrium abundance of this particle goes exponentially suppressed. Now, in order to see that this is not always the case, we are just focusing on one simplified model for dark matter that belongs to a broader class, where the dark matter is a singlet under the standard model gauge groups, but there is a mediator which is charged under the standard model gauge group. And in particular here, we stick to the case where the mediator is a scalar charge under QCD and U1. So these models are quite studied, especially in the context of freeze out. Here you see the Lagrangian. Basically, you have this dark matter interaction with quarks through the mediator eta. And this is the construction of the Lagrangian, and that dictates the form also of the quantum numbers in terms of Yukawa and hypercharges for the eta. Here, the eta is slightly heavier or much heavier than the dark matter in order for the mediator to decay into the dark matter, and instead the dark matter is absolutely stable. Now, we picked this model also because other studies of freezing were already made, so that we have some comparison to do. And according to our assumption, so very small Yukawa couplings here, why we will achieve freezing, we start with very large temperatures, larger than any other mass scale in the problem, which is the mass of the eta by assumption. And we refrain ourselves to be smaller than temperature of the electroweak phase transition, because I will comment later on that this would take then other challenges to look at. In this case, dark matter never reaches thermal equilibrium. However, these two other particles are maintained in equilibrium from the standard model interactions. And the simple process that you can think of is the decay of the scalar into the quark into dark matter that will induce the freezing production of dark matter. My point is that we are going to see that for this model specifically, and from, I would say, other models which are pretty similar in the constructions, there is a contribution from the high temperature regime, which is important for the dark matter production for freezing. And the approach that I'm going to use is actually borrowed from thermal leptogenesis, which have been quite extensively developed also for the freezing case. And the main point is that we have a very weakly coupled field, which is the chi, and it is coupled to an equilibrated path, meaning the particles, the eta and the quark, which are kept in equilibrium with the standard model surrounding path. Now, the point is that the rate of change of this dark matter particle can be expressed through an evolution equation, where this is the single particle phase space distribution, and this is my key ingredient here, which is called particle production rate, that can be at all orders in G, at first orders in Y, be expressed in terms of a two-point field correlator, so the self-energy of the chi here. And these two fields are the one that I have available for constructing my simple one-loop self-energy diagram. Often in what follows, I will express the production rate in terms of the imaginary part of the retarded correlator, which is one of the correlators that you have at final temperature. So very naively, at zero temperature, you would imagine to cut this correlator here and have some of the processes available. I will show later. The good point of this approach is that when you do perturbative expansions and you work in the simplest scenario, you recover the Boltzmann equation. However, this is a field theoretic approach at finite temperature, so you can start including basically as much as you want in the description. Now, in order to make contact with the Boltzmann formalism, as I said, imagine to have the one-loop self-energy diagram here. And according to the various cuts you can do at finite temperature, you have these many processes. In particular, 3 of these can be realized kinematically according to what happens to the in-vacuum masses in your model. So in our case, we have the mass of the eta being larger, the mediator being larger of the sum of the dark matter mass and the quark. So this process is the one that gets realized. And if you compute the imaginary part of the retarded correlator, that I will call from here Born correlator, Born production rate, sorry, for this 3-level diagram, you already see that you are obtaining something close to what you obtain in a Boltzmann description. So when you integrate the evolution equation that I showed you before, you're just getting the number density of the dark matter, which is triggered by the decay of this scalar. And you see that the distribution for the boson, so for the eta and the quark, appear as they would do in a Boltzmann-like treatment. You don't have anything here for the produced Majorana fermion because it is assumed far away from equilibrium. So this comes out from the formalism indeed. Now, the first thing that you want to, and you can think of changing when you want to look at a high temperature regime is to have a look at the thermal masses. Thermal masses appears because of repeated and many interactions of the particle in the medium. And these are ingredients that one may want to introduce, especially when the temperature are much larger than the in-vacuum mass scales. These are the asymptotic thermal masses for the quark, and there is one also for the eta in the large temperature limit. Actually, 2 years ago, Frisin produced dark matter in connection with the thermal masses was discussed in this conference. And there is no thermal mass for the Majorana fermion what is the impact on the Born production rate, with or without including the thermal mass. Here in the plot on the left, you see the production rate normalized by the temperature, and you see that the vacuum born overshoots by quite a sizable quantity the born with the thermal mass. It's basically because you are shrinking the final state phase space for the two particles produced because of the effect of thermal masses. And this is what happens for the dark matter energy density. You see this is reflected here. In the case that you include only thermal mass in the process as a high temperature dynamics, you would then get less dark matter because the production mechanism is less effective. Nevertheless, you do not get anything new here from the point of view of this kind of freezing models bringing infrared freezing, because again, the production of the dark matter basically is related to this low temperature window. However, the thermal masses are not the only processes and effects you can think of at high temperature. In particular, if you go to very large temperatures, the typical momentum of the particle is indeed the temperature itself, much larger than the in vacuum and also the thermal masses. That scales like GT, as I showed before. And a synonym of high temperature dynamics is that you have a collinear kinematic. So these processes are basically collinear. The angles between the produced particles and the initial and the produced particles is small. And then what happens is that if you start including the stimulation from the plasma, like this 2-to-2 scattering with the light plasma constituent via soft momentum exchange, well, then the collinearity of this process does not change. And despite this seems suppressed because the appearance of these two vertices here in the particular kinematic condition we are speaking about, this is not suppressed. And actually you can add more and more of this scatterings with the charged particles involved, and this process is going to be basically living order, and actually it's going to drive the production of the Majorana fermion at high temperature. So the point is that you have a long formation time, and many of these scatterings may happen before the Majorana fermion is produced. So this is again something that we are borrowing from thermal leptogenesis and also at QCD. The way that you resum this kind of infinitely many rank in the self-energy of the Majorana fermion goes under the name of Landau-Pomerachuk-Mida resummation that allows you to take this process into account, and we make here the connection with the self-energy that I showed you before. Without going to the technicalities, now, instead of having just one process for the production of the Majorana fermion high, you have these many processes that happen at the same time, and you can take into account by the LPM resummation. In the following, I will just refer to them as 1 to 2 effective processes, because you have many of these external legs that I showed before here. So you do not only have the decay of the eta into the dark matter and the quark, but also the decay of the quark into the eta and to the fermion, and also the quark and the eta, giving us a Majorana fermion. And this is the outcome in terms of the plots that I showed before. So the temperature again is increasing from left to right. You see that the Born rate with full thermal masses is the it's the red line here, which is similar to what we had before. However, at high temperature now, the green dotted line is the effect of the LPM production rate, which is very much larger than the Born rate. Spoiler alert, you will not see many order of magnitude difference in the production of the dark matter, because this is a high temperature regime, and so you have to compete with the Hubble at the end of the day. But anyhow, it is something that you do not see if you do not include these high temperature dynamics. And the fact that here at small temperature this line is increasing is actually a fake announcement, because it tells you that you are insisting on assuming a collinear kinematic where you start instead to be sensitive to the in-vacuum thermal masses, to the in-vacuum masses here. So you have to restore the full kinematic. You cannot be just collinear in this region. And what we do in order to take our best effort curve, which is the black solid line here, is to subtract to the LPM Born, so the one which contains the collinear kinematic, but no scatterings with the thermal plasma, basically because you are killing these soft interaction at small temperature. So in this case, you see that this difference then aligns well with the Born, which gives the correct or more correct expression at small temperature. So on top of these 1 to 2 effective processes for the model at hand, you have many 2 to 2 scatterings that contributes to the production of the dark matter here. And here I just lit some of the diagrams you can think of. And these diagrams have been included in some derivation of the freezing dark matter production for this very model when the temperature is of the order and smaller than the dark matter mass of the scalar mass. Here we are doing that for the high temperature regime, and again we can build up on the developments in thermal leptogenesis. The point is that when you consider all these diagrams here, you have two momentum contributions that comes in, the hard momentum contribution, which cause no problem. However, when the quark exchange here is soft, and you are at high temperature, well, then you are going to hit an infrared divergence. This can be cured by including also for the quark a thermal mass, which is actually quite natural when you are going here with a soft momentum that basically probe this kind of scales, and this is exactly the scale of the thermal mass for the quarks as well. So the main message here is that some T-channel diagrams have an infrared divergence for small momentum q. You can subtract it and then add up the correct contribution from the same diagrams, but with an thermal loop propagator for the quark. So this is going to be the summary of the rates I'm going to use in the next plot. So basically you have the total rate as the sum of the 1 to 2 effective process and the 2 to 2 scatterings regularized, as I said before. And the difference between the dot and continuous line is our way to somehow deal with the lack of knowledge of the next living order rates. So the 1 to 2 effective process that you would compute in this regime here, in the relativistic regime, when the temperature is of the order of the masses, of the in-vacuum masses involved. This calculation is much more challenging, as state of art does not give us such a calculation for two massive particles, the dark matter and the mediator. So we do it by suppressing with a susceptibility, which basically is a very conservative way of killing off the effect of the high temperature, because you exponentially suppress basically the effect of this eta. So as soon as you have temperature of the order of the largest in vacuum mass scale, you are getting them exponentially suppressed. So the solid black line is our best effort curve again, and this is what I will be using in the next plots that I'm showing. So this is again the plot for the dark matter energy density, and here I'm comparing with the blue line, which is the one obtained with the Born production rate, as I showed before. The red line is the Born production rate with the thermal masses included, and instead you see the black solid line, which reproduces the observed relic density. And the point is that for temperature larger than the mass of the eta particle here, which is at 5 TeV for this benchmark point, you see that a non-negligible production for the dark fermions already happened because of this high temperature contribution that I showed before, basically the 1 to 2 and the 2 to 2 scatterings. So with the same parameters here, you are underestimating the relic density if you use the in vacuum and the Born rate with the full thermal masses. Now, we didn't do a scan of the parameters. We just developed some sense about what is important. And the main parameter that we find to say draw a line between this effect being very important, this effect being rather relevant or less relevant, is the mass splitting between the mediator and the dark matter mass. So when you have a relative mass splitting of 1/10 of the dark matter mass, you are basically very sensitive to the reduction of the phase space in the Born production rate, because you have the produced particle close in mass with the parenting decaying particle. And this is something that at high temperature, you are basically not seeing. So at high temperature with the multiple soft scatterings, this kind of suppression given by the mass splitting is not important. And that's why you are getting a very large suppression if you just compute with these parameters here the dark matter energy density. So this is almost an order 10. And you see that if you include the thermal masses, I mean the thermal masses for the bond rate, you are basically producing nothing because this is even more shrunk. In the case, the relative mass splitting is 10 times the mass of the dark matter. The bond rate suffers less because you have an open and wider phase space for the particle decay, and the correction would be a order of 20% or so. The dot dashed line is our theoretical estimation for the error we are committing by not knowing the next leading order effect, which in any case is roughly, I would say, smaller than the effect you are seeing by non-accounting for the high temperature dynamics. Now, a very brief comment before concluding. As I said, the same model has been studied for freezing, and since you have this eta, which is a color particle, but with this coupling y being very small because of the freezing requirement, then you have long-lived particles that can be somehow studied at colliders, in particular in the form of hadrons. And then you can put some limits in the parameter space of the mass of the dark matter and the splitting, which is given by this LHC constraint on the search of these stable long-lived particles. And what I want to say is that then these green lines are the corresponding relic density calculation for the freezing produced dark matter, which can be very off, especially in some parameter space. I mean, when the splitting is of the order or smaller than dark matter mass. I mean, can be order 1 correction and also up to an order of magnitude that you may want to consider. So let me come to the summary of the talk. We studied the impact of the ultra-relativistic or high temperature regime for a particular model belonging to a broader class of the simplified models for dark matter. And in this case, you have very normalizable operators that implement the interaction between the dark matter and the standard model particles through a mediator, which is also charged under the standard model gauge group. And with this kind of operators, you do expect to have the bulk of the dark matter production at temperature of the order of the in-vacuum masses. But we show that this is not always the case. I mean, you may have high temperature contribution that gives order 1 contribution. For the particular model we have studied and for the particular benchmark points, because we didn't do an extensive parameter space study, the effect can range from 1 order of magnitude to 20% if you take the mass split, the relative mass splitting with respect to dark matter of 1/10 or 10. And I would say that these high temperature effects may affect models which have a similar construction to ours. I list some of these models in the backup slides. And I would like to stress that our main uncertainty comes from the knowledge, from the fact that we don't know the next leading order rates in the relativistic regime, which is actually the point where you have the peak of the production in these freezing models here. So it would be important to address this kind of rates in this temperature regime. And this is what we try to estimate with our theoretical uncertainty in a conservative way. Thank you.
It's for the first timing also. Any questions inside the room? Well, let us check online if there's any. Okay. Therefore, we're going to go to coffee break. Let's thank the speaker again.